Hello and welcome to the channel. Please welcome an equation that has to be solved for integer values of x and y. Such an equation is called a Diophantine equation. There are standard methods of solving a linear Diophantine equation, where both x and y have degree 1. A linear Diophantine equation typically has an infinite number of solutions involving a parameter. For a Diophantine equation of degree more than 1, there is no standard method to cover all cases. However, if we somehow can limit an unknown value to a finite set of integers, we can test each integer in this set and find all the solutions. Of course, the set must be small enough, otherwise it may take ages. We can see that the left-hand side of the given equation is a quadratic polynomial. So, if we can restrict possible values of y to a finite set, each possible value will give a quadratic equation, which can be easily solved. In fact, the solution will be much easier than someone may think, since the left-hand side can be represented as the product of two consecutive integers. So, for a given value of y, we evaluate the right-hand side, represented as the product of two consecutive integers, and immediately find the value of x. Amazingly enough, the right-hand side also allows factorization, which also contains a product of two consecutive integers. A nice picture is spoiled by the third factor, y squared plus 1. However, since this factor is always positive, we can equate each side to 0. In this case, both x and y must be either 0 or negative 1. Combining these values gives 4 solutions of the equation. However, even though 4 solutions is more than nothing, this doesn't help much, since we are looking for all solutions of the equation, while the question about the existence of other solutions still remains open. It will be great if you can suggest a way of solving the equation based on this factorization, as the solution I am going to present here uses a completely different idea. So please pause the video and see what you can do. The solution discussed here can be hardly called elegant, however it uses a rather unusual idea, which I believe can be useful for other Diophantine equations of degree 2 and up. As start, let's multiply the equation by 4, then add 1 to both parts. The left-hand side is of course 2x plus 1 all squared, however how to trace the right-hand side is not quite clear, hence we just copy it. Now let's explore the right-hand side. The first impression is grouping the terms with even degrees of y. They give 2y squared plus 1 all squared, while for the remaining two terms we get 4y times y squared plus 1. A perfect square start is really what we need, however, since y squared plus 1 is always positive, the second term has only one root, y equals 0. This means that the second term is non-negative when y is non-negative and negative when y is negative. We see that both ranges for y are infinite, while the method which is going to be applied here requires one range to be finite. This means that we need to apply another grouping. This time we are going to get a perfect square out of first 3 terms. To do that, we split 4y squared into y squared and 3y squared, and get a sum of 2 polynomials with 3 terms in each. In the first polynomial, we factor out y squared. The second polynomial can be also factorized by representing 4y as 3y plus y. The expression in the first bracket is of course 2y plus 1 all squared. And let's factorize the second polynomial as well. The first term is a full square. To make that obvious, we can rewrite it as 2y squared plus y all squared. And let's denote the second polynomial as g of y. G of y is a quadratic polynomial having 2 roots. Let's write them in increasing order. Y sub 1 equals negative 1, y sub 2 equals negative 1/3. Therefore, g of y is positive if either y is less than negative 1 or y is more than negative 1/3, and g of y is non-positive if y belongs to the closed interval from negative 1 to negative 1/3. Now, non-negative values of g correspond to a finite range, which is what is needed. Moreover, this range contains a single integer, negative 1. Therefore, if y is an integer other than negative 1, g of y is positive. Since y is assumed to be an integer, we can write without loss of generality that g of y is greater than 0 if y is different from negative 1. Now it's time to recall what it is all about. We have an equation containing 2x plus 1 all squared in the left-hand side. The right-hand side of the equation can be expressed as 2y squared plus y all squared plus g of y. We have seen that g of y is positive when y is different from negative 1. Therefore, 2x plus 1 all squared is greater than 2y squared plus y all squared if y is not equal to negative 1. Let's copy this valuable inequation to the top and wipe out no longer valuable stuff on the page. Such a cleanup is extremely important, because it isn't quite obvious how the obtained inequation can help in solving the given equation. Now, as we've got plenty of space, let's use it to evaluate the next square after the right-hand side. That will be 2y squared plus y plus 1 all squared. The square of a polynomial is the sum of squares of all its terms, as well as all pairwise products of the terms doubled. This may look really complex for some ones, however, for a trinomial we have just 6 terms. So let's apply the formula to our trinomial. Here are the squares and pairwise products doubled. Now let's subtract for the obtained equation the equation for 2x squared plus 1 squared. After expanding the brackets and huge cancellation, we end up with just y squared minus 2y, and name it h of y for short. Using this notation, we can write 2x plus 1 all squared is equal to the square of 2y squared plus y plus 1 minus h of y, where h of y can be expressed as y times y minus 2. We see that h of y has 2 roots, and we again write them in increasing order. Y sub 1 equals 0, y sub 2 equals 2. Next, we write that h of y is positive if either y is less than 0 or y is greater than 2, and h of y is non-positive when y belongs to the closed interval from 0 to number 2. Again, there is a finite range for non-positive values of a polynomial. For other values, h of y is positive. In other words, h of y is greater than 0 if y is outside the closed interval from 0 to number 2. In the equation for 2x plus 1 squared, h of y is subtracted. Therefore, 2x plus 1 squared is less than 2y squared plus y plus 1 all squared for y not belonging to the closed interval from 0 to number 2. We've got another precious equation for 2x plus 1 squared, which we, of course, also copy to the top. Believe me or not, the toughest part is left behind, so try to complete the solution on your own. Let's unite the two inequations for 2x plus y squared into a double inequation. The double inequation holds if both previous inequations hold. That is, y is different from -1 and does not belong to the closed interval from 0 to number 2. Adding -1 to the closed interval from 0 to number 2 gives closed interval from -1 to number 2. So the double inequation holds if y is outside this interval. Take a first look at the double inequation. Somehow, the square of an integer sneaked between the square of two consecutive integers without being equal to any of those. Of course, this may happen only in a surreal world, while we are supposed to be realistic. Therefore, the given equation may have solutions only if the double inequation doesn't hold, which means that y must belong to the closed interval from -1 to number 2. The only thing remained is testing each integral value of y in this interval. In fact, two values of y have been already processed. We've seen that if y equals -1 or 0, the right-hand side of the equation becomes 0. Therefore, its left-hand side, which can be expressed as x times x plus 1, must be also 0. In this case, x is either -1 or 0. Assuming y equal to 1, we get 4 in the right-hand side. Number 4 cannot be represented as a product of two consecutive integers. Therefore, there are no solutions for y equals 1. Finally, if y equals 2, the right-hand side is 30. There are two ways to represent 30 as a product of two consecutive integers: 5 times 6 or -6 times -5. This gives two possible values of x for y equals 2, -6 and 5. So the answer consists of 6 xy pairs, 2 pairs where y is -1, 2 pairs where y is 0, and 2 pairs where y is 2. Now we can formulate the method used for solving this equation. Place the square of an integer strictly between the squares of two consecutive integers. The impossibility of that restricts one of the unknown values to a finite set of integers, which is reasonably small to test each integer of the set and find all the solutions of the equation. Thanks to everyone who has the patience to watch the video till the end.